I'm going to talk to you guys about systems. And systems are a pretty easy concept to understand, but they're critical for understanding momentum and energy when you're talking about objects that are in groups, particularly objects that are in groups that interact with each other. And so you may remember the concept actually from chemistry, because chemistry has to deal with systems as well. And so you're oftentimes analyzing whether a system is open or closed or isolated in chemistry to be able to make some conclusions about the things that you're analyzing. Like, for example, if you have a calorimeter, for example, one of the things that you have to remember with a calorimeter is that you want the system to be as isolated as possible so that you can gather together and measure all the heat that you're producing to be able to find out how much heat energy is contained in the object or the substance that you're dealing with. So in physics, it's exactly the same thing. We have three systems, and so you can see here that the systems are either open or closed or isolated. And so for an open system, you can see here that the energy and matter are able to leave the system. I would also put in physics that it is possible, although it's unusual, it is possible for energy to go back into the system or for matter to go back into the system. I'm going to symbolize it with an M there. But that's not usual, right? So usually even middle school students will develop an experimental method that, even though it's open, will not allow mass to go back in and will not allow energy to go back in. You wouldn't, for example, measure a collision between two cars while, let's say, somebody from the outside was giving one of the cars a pull with a rope, because then it makes it more difficult to analyze what's actually happening. If you're talking about how the energy is transferred from one car to another, you don't want to add in energy that's unspecified from some other source, like, for example, someone pulling a rope. And so typically we don't see that, but it can happen if you're not careful about how you develop your experimental design. On the other hand, typically in the physics classroom, we use a closed system. And closed systems do allow energy out, but they do not allow energy in for the reason I was talking about just a minute ago. Typically, the energy that they allow out is usually thermal energy, right? And it's because of friction. And so as much as we would like to, in a perfect world, say that we have ideal conditions, we do not. And so friction is going to take kinetic energy and convert it into that thermal energy. And that thermal energy leaves the system as it bleeds off into the air, right? So when two things collide, they make sound and they make heat. And if they collide fast enough, they make light. But if you think about it, sound and heat are both sort of a thermal energy because they both have to do with the vibrations of the air particles. And so that amount of energy is leaving the system, and there's not really an easy way for us to measure that usually. On the other hand, in a perfect world, we'd have a totally isolated system in which you have this barrier between the stuff that you're measuring and the rest of the world. There may be heat that's leaving one object, but it must be accounted for going into something else. And so there is a sort of an iron wall between the two. But even more than that, because you've got your objects inside, and even iron would allow heat to go across it. And so we have to assume that there's some sort of insulation in between the system inside and the environment outside. So outside of the system is this environment. Typically, we in physics will assume that there's no loss of energy to the environment, but we know, I guess, we do that assumption to try to make our math easier, knowing full well that there probably is a little bit. And if you're good about your way you design an experiment, you can use a closed system as if it was an isolated system by limiting the amount of energy that leaves. Typically that's done by either using very slow speeds, so there's very little kinetic energy which can be converted into thermal energy, or we do it over a very short period of time, and so the amount of energy that's allowed to escape over that short period of time is not very much. because we limit the time. And so we pretend it's isolated even though we know it's really closed. And so I may slip a couple of times and say that we have a closed system, but what I really mean is that we are approximating an isolating system, usually. What you don't want is to develop an experiment in which you have an open system. And typically, as someone who used to run science fairs with middle school students, typically they're always open systems. That's how you know that someone doesn't really understand the scientific process, is that they have decided an open system is okay to make scientific conclusions with. Sometimes you can't get away from it, but most often, at least in physics, most often you can approximate an isolated system using a closed system under certain conditions. Okay, that's all I got. Thanks for watching.